You know, in engineering, it's often the simplest ideas that are the most powerful. Today, we're going to pull back the curtain on one of those, an engineer's secret weapon called the Principle of Transmissibility. It's a concept that lets us simplify what look like incredibly complex problems.
So, to really wrap our heads around this, let's kick things off with a little thought experiment. Don't worry, no crazy math just yet. This is all about intuition.
Okay, so picture this. You've got a heavy table you need to move, and you've got this super long, really stiff rod to do it. The goal is just to slide the table straight forward. So here's the question. Does it actually matter where you push on that rod?
All right, scenario 1. Let's say you stand a good 5 feet back and you push on the end of the rod. The rod pushes on the table and, well, the table slides forward. Exactly what you'd expect, right?
Okay, now for scenario 2. What if you walk right up to the table and push on the rod right where it's touching the wood? What happens then? Well, the table, it slides forward in the exact same way. The end result, the motion of that table, is completely identical.
And that right there, that's the whole key. As long as your push stays on that same straight line, which we call the line of action, the table has no idea where the force is coming from. It only feels that push along that one specific line.
So what we just did with that table and rod, that's not just a random puzzle. It's the intuition behind a really core principle in mechanics. This is where we get a little more formal and start thinking of a force as a sliding vector.
First things first, there's one really crucial idea we have to agree on. This whole principle only works for what engineers call a rigid body. Now, in the real world, pretty much everything bends or squishes a little bit. But for analyzing something like a big steel beam, it's a super useful shortcut to assume it doesn't deform at all. And that brings us to the main event, the principle of transmissibility. All it really says is that we can take a force and slide it anywhere we want along its line of action. As long as we're dealing with a rigid body, the external effects, whether the object moves or the forces holding it in place, are going to stay exactly the same.
This is what's so cool about it, right? It's a total shift in how you think about a force. We usually imagine a force happening at one specific point. But with rigid bodies, it's way more useful to think of that force being defined by its strength, its direction, and that all-important line of action.
Okay, neat concept, but why do we care? Why is this a secret weapon? Well, because it's an absolutely incredible shortcut for the math. It saves a ton of time and, honestly, helps prevent a lot of headaches and mistakes. Let's see how.
This trick really shines when you have to calculate moments. And a moment is just the fancy engineering term for the turning effect of a force. Like when you use a wrench to tighten a bolt. That's you creating a moment.
Now look over here on the left. This is the hard way. The force is applied at some weird, awkward spot, and figuring out its turning effect is going to require some messy geometry. But now, check out the right side. We just use our principle. We slide that force along its line of action to a much nicer spot, maybe where it crosses the x-axis, and boom! The math suddenly gets way simpler. But the answer? It's exactly the same. This is a huge aha moment for engineers.
So it really boils down to this simple 3-step playbook. Find the line, slide the force to a point that makes your life easy, and then solve. It can turn a really nasty-looking problem into something you can solve in a snap.
Now, like any powerful tool, you got to know the rules. This isn't just magic. The principle of transmissibility has some very specific limits, and you absolutely have to respect them.
So here are the big ones. First, this only works for external effects. If you slide that force, the stress inside the object will definitely change. Second, remember, this is for our idealized rigid bodies only. And, probably most important of all, that force has to stay on its original line of action. No cheating.
So that probably gets you thinking, right? What if you do need to move the force to a point that isn't on its line of action? Can you even do that?
And the answer is yes, you can. But it's a totally different move. To make sure the external effects stay the same, you have to add something called a couple moment. It's basically a pure turning force to make up for the move. That's a whole other topic, but it really shows just how important that line of action is.
All right, let's pull this out of the textbook and back into the real world. This abstract little trick isn't just for exams. It's fundamental to how we build and analyze the massive structures that you see every single day.
Think about a giant construction crane. The forces in those cables are huge, and they're pulling at all sorts of complicated angles. By using the principle of transmissibility, engineers can simplify that whole system of forces to make sure the crane is stable and won't tip over. It basically makes impossible math possible.
And it's not just cranes. You see the same idea at work in the trusses of a bridge or the complex frame of a transmission tower. This principle lets engineers get a handle on all those forces, making sure the structures we rely on are safe.
And this really hits on what R.C. Hibbeler, who wrote one of the classic engineering textbooks, said. The best way to really get these ideas is to get your hands dirty and solve problems. This isn't just theory, it's a tool you use.
The principle of transmissibility is just one of these elegant, simple cheats that engineers have up their sleeves. It kind of makes you wonder, doesn't it? What other little physics hacks are out there, hiding in plain sight, making our whole complex world work? Thanks for joining me.